Let us take another example, hemophilia. Hemophilia, just like color blindness, is also an example of sex-linked inheritance. It is a disorder associated with blood. A disorder associated with blood. The characteristic situation here is there is a delay in the clotting of blood. There is a delay in the clotting of blood. Depending upon the intensity of the injury, blood clots anywhere between few minutes to 1 or 2 hours. But in persons with hemophilia, there is a delay in the clotting of blood. Even from a small injury, blood continues to flow out. This delay is due to the absence of one of the factors responsible for clotting of blood. One of the factors responsible for clotting of blood called anti-hemophilic factor, commonly abbreviated as AHF. AHF is just one of the 13 factors that are involved in the clotting of blood. AHF, anti-hemophilic factor, will not be present. Therefore, there is a delay in the clotting of blood. The absence of AHF is the result of the expression of a recessive gene. So when the recessive gene present on the X chromosome, when this recessive gene present on the X chromosome expresses, anti-hemophilic factor is not produced. There is a corresponding allele for this, and that allele, which is also present on the X chromosome, is responsible for production of AHF. Therefore, normal clotting of blood. The situation is exactly similar to what we have seen in color blindness. Hemophilia is more common in males. More common in males and expresses in females only in the homozygous recessive condition. And just like color blindness, hemophilia is also an example of crisscross or zigzag inheritance, also called skip generation inheritance. Again, another important situation in hemophilia is that it is commonly called royal disease, because hemophilia has very frequently affected the royal family of Europe. In fact, the situation that we see in the royal family of Europe, like for example Britain, is that the prince is not given the throne, the princess is given the throne, because the prince used to die for some or the other reason due to hemophilia. Again, let us begin with the situation. A woman with normal clotting of blood XX marries a hemophiliac man XHY, H representing gene responsible for hemophilia. Ovum will be X, sperm can be either XH or Y. If these two fuse, it will be XXH. If these two fuse, it will be XY. Both the children, male and the female, will be normal, but the female will be carrier, male will be normal. So carrier female, normal male. Suppose this carrier female marries a normal male. XH, XY. We are taking the same genotype. Gametes, it can be either X or XH, and here X and Y. So possible combinations X, Y, X, XH, this into this, XX, this into this, XXH, this into this, XY, this into this, XHY. These are the four possibilities. XX is normal female, XXH carrier female, XY normal male, XHY hemophiliac male. So again you can see the gene responsible for hemophilia was present in the father. From the father it has been passed on to his daughter. From the daughter it may come to her daughter or her son. In the daughter it does not express, but in the son it expresses. So again it is an example of crisscross inheritance. Suppose this carrier female XXH marries a hemophiliac male XHY. Now the possibility is XH here, XH and Y here, X and XH, X and Y, this into this, XX, this into this, XXH, this into this, XY, this into this, XHY. So what are the possibilities now? XX normal female, XXH hemophiliac female, XY normal male, XHY hemophiliac male. So gene can be passed on to either male or female if it is present in both the X chromosomes, XH, then hemophilia can express in females. If hemophilia expresses in females, such females die at puberty because at the time of menstruation there is loss of blood, clotting does not occur easily, so it may result in death.